Exercises pages 73 to Chapter 4. Laws of Motion. Exercises pages 73 to 77. Exercises Q1. Page 73. Choose the correct answer. Consider the following pair of forces of equal magnitude and opposite directions. P. Gravitational forces exerted on each other by two-point masses separated by a distance. Q. Couple of forces used to rotate a water tap. R. Gravitational force and normal force experienced by an object kept on a table. For which of these pairs the two forces do not cancel each other's translational effect? 1. Only P2. Only P and Q3. Only R4. Only Q and R. Solution. Only P, i.e., gravitational forces exerted on each other by two-point masses separated by a distance. Exercises Q1. Page 73. Choose the correct answer. Consider following forces. W. Force due to tension along a string, X. Normal force given by a surface, Y. Force due to air resistance, and Z. Buoyant force or upthrust given by a fluid. Which of these are electromagnetic forces? 1. Only W, Y and Z. 2. Only W, X and Y. 3. Only X, Y and Z. 4. All 4. Solution. All 4. Exercises Q1. Page 74. Choose the correct answer. At a given instant, three-point masses m, 2 meters and 3 meters are equidistant from each other. Consider only the gravitational forces between them. Select correct statement, S for this instance only. 1. Mass m experiences maximum force. 2. Mass 2 meters experiences maximum force. 3. Mass 3 meters experiences maximum force. 4. All masses experience force of same magnitude. Solution. Mass 3 meters experiences maximum force. Exercises Q1. IV page 74. Choose the correct answer. The rough surface of a horizontal table offers a definite maximum opposing force to initiate the motion of a block along with the table, which is proportional to the resultant normal force given by the table. Forces F1 and F2 act at the same angle t with the horizontal, and both are just initiating the sliding motion of the block along with the table. Force F1 is a pulling force while the force F2 is a pushing force. F2 greater than F1, because 1. Component of F2 adds up to weight to increase the normal reaction. 2. Component of F1 adds up to weight to increase the normal reaction. 3. Component of F2 adds up to the opposing force. 4. Component of F1 adds up to the opposing force. Solution. Component of F2 adds up to weight to increase the normal reaction. Exercises Q1. B page 74. Choose the correct option. A mass 2 meters moving with some speed is directly approaching another mass m moving with double speed. After some time, they collide with a coefficient of restitution 0.5. The ratio of their respective speeds after the collision is 1, 2, 3, 2, 3, 2, 3, 2, 4, 1/2. Solution. 3/2. Exercises Q1. B page 74. Choose the correct answer. A uniform rod of mass 2 meters is held horizontal by two sturdy, practically inextensible vertical strings tied at its ends. A boy of mass 3 meters hangs himself at 1/3 length of the rod. The ratio of the tension in the string close to the boy to that in the other string is 1, 2, 2, 1.5, 3, 4, 3, 4, 5/3. Solution. 1.5. Exercises Q1. B page 74. Choose the correct answer. Select the wrong statement about the center of mass. 1. Center of the mass of a C-shaped uniform rod can never be a point on that rod. 2. If the line of action of a force passes through the center of mass, the moment of that force is 0. 3. Center of a mass of our Earth is not at its geometrical center. 4. While balancing an object on a pivot, the line of action of the gravitational force of the Earth passes through the center of mass of the object. Solution. While balancing an object on a pivot, the line of action of the gravitational force of the Earth passes through the center of mass of the object. Exercises Q1. B. Page 74. Choose the correct answer. For which of the following objects will the center of mass not be at their geometrical center? I. An egg. 2. A cylindrical box full of rice. 3. A cubical box containing assorted sweets. 1. Only I. 2. Only I and 2. 3. Only 3. 4. All I. 2 and 3. Solution. All I. 2 and 3. Exercises Q2. I. Page 74. Answer the following question. In the following table, every entry on the left column can match with any number of entries on the right side. Pick up all those and write respectively against I, E, E, and IB. Name of the force. Type of the force. A force due to tension in a string. PM force. B normal force. Q reaction force. C frictional force. R conservative force. D resistive force offered by air or water for objects moving through it. S non-conservative force. Solution. A force due to tension in a string. Electromagnetic EM force, reaction force, non-conservative force. B normal force. Electromagnetic EM force, non-conservative force, reaction force. C frictional force. Electromagnetic EM force, reaction force, non-conservative force. D resistive force offered by air or water for objects moving through it. Electromagnetic EM force, non-conservative force. Exercises Q2. E. Page 74. Answer the following question. In real life, objects never travel with uniform velocity, even on a horizontal surface, unless something is done. Why is it so? What is to be done? Solution. 1. According to Newton's first law, for a body to achieve uniform velocity, the net force acting on it should be 0. 2. In real life, a body in motion is constantly being acted upon by resistive or opposing force like friction, in the direction opposite to that of the motion. 3. To overcome these opposing forces, an additional external force is required. Thus, the net force is not maintained at 0, making it hard to achieve uniform velocity. 4. For an object to travel with uniform velocity, the surface has to be frictionless, i.e., the motion has to be free of resistive or opposing forces. Exercises Q2. E. Page 74. Answer the following question. For the study of any kind of motion, we never use Newton's first law of motion directly. Why should it be studied? Solution. 1. Newton's first law shows an equivalence between the state of rest and state of uniform motion along a straight line. 2. Newton's first law of motion defines force as a physical quantity that brings about a change in state of rest or state of uniform motion along a straight line of a body. 3. Newton's first law of motion defines inertia as a fundamental property of every physical object by which the object resists any change in its state of rest or of uniform motion along a straight line. Due to all these reasons, Newton's first law should be studied. Exercises Q2. IB page 74. Answer the following question. Are there any situations in which we cannot apply Newton's laws of motion? Is there any alternative for it? Solution. 1. Limitation. Newton's laws of motion cannot be applied for objects moving in a non-inertial, accelerated frame of reference. Alternative solution. For a non-inertial, accelerated frame of reference, pseudo-force needs to be considered along with all the other forces. 2. Limitation. Newton's laws of motion are applicable to point objects and rigid bodies. Alternative solution. Body needs to be approximated as a particle as the laws can be applied to individual particles in a rigid body and then summed up over the body. 3. Limitation. Newton's laws of motion cannot be applied for objects moving with speeds comparable to that of light. Alternative solution. Einstein's special theory of relativity has to be used. 4. Limitation. Newton's laws of motion cannot be applied for studying the behavior and interactions of objects having atomic or molecular sizes. Alternative solution. Quantum mechanics has to be used. Exercises Q2. B page 75. Answer the following question. You are inside a closed capsule from where you are not able to see anything about the outside world. Suddenly you feel that you are pushed towards your right. Can you explain the possible cause S? Is it a feeling or a reality? Give at least one more situation like this. Solution. 1. In a capsule, if we suddenly feel a push towards the right, it is because the capsule is in motion and taking a turn towards the left. 2. The push towards the right is a feeling. In reality, when the capsule is beginning its turning motion towards the left, we continue in a straight line. 3. This happens because we try to maintain our direction of motion while the capsule takes a turn towards the left. 4. An external force is required to change our direction of motion. In accordance with one of the inferences from Newton's first law of motion, in the absence of any external force, we continue to move in a straight line at a constant speed and feel the sudden push in the direction opposite to the motion of the capsule. 5. Example. While traveling by bus, when the bus takes a sudden turn, we feel the push in the opposite direction. Exercises Q2. B page 75. Answer the following question. Among the four fundamental forces, only one force governs your daily life almost entirely. Justify the statement by stating that force. Solution. 1. The electromagnetic force is the attractive and repulsive force between electrically charged particles. 2. Since electromagnetic force is much stronger than the gravitational force, it dominates all the phenomena on atomic and molecular scales. 3. The majority of the forces experienced in our daily life, like friction, normal reaction, the tension in strings, elastic forces, viscosity, etc., are electromagnetic in nature. 4. The structure of atoms and molecules, the dynamics of chemical reactions, etc., are governed by electromagnetic forces. Thus, out of the four fundamental forces, the electromagnetic force governs our daily life almost entirely. Exercises Q2. B page 75. Find the odd man out. 1. Force responsible for a string to become taut on stretching. 2. Weight of an object. 3. The force due to which we can hold an object in hand. Solution. Force responsible for a string to become taut on stretching, weight of an object, the force due to which we can hold an object in hand, weight of an object. Reason. Weight of an object, force due to gravity, is a non-contact force, while force responsible for a string to become taut, tension force, and force due to which we can hold an object in hand, normal force, are contact forces. Exercises Q2. B page 75. Answer the following question. You are sitting next to your friend on ground. Is there any gravitational force of attraction between you two? If so, why are you not coming together naturally? Is any force other than the gravitational force of the Earth coming in the picture? Solution. Exercises Q2. XA page 75. Answer the following question. Distinguish between real and pseudo force. Solution. Real force. Pseudo force. 1. A force which is produced due to interaction between the objects is called real force. A pseudo force is one which arises due to the acceleration of the observer's frame of reference. 2. Real forces obey Newton's laws of motion. Pseudo forces do not obey Newton's laws of motion. 3. Real forces are one of the four fundamental forces. Pseudo forces are not among any of the four fundamental forces. 4. Example. The Earth revolves around the Sun in a circular path due to the gravitational force of attraction between the Sun and the Earth. Example. Bus is moving with an acceleration a, on a straight road in forwarding direction. A person of mass, m, experiences a backward pseudo force of magnitude, ma. Exercises Q2. XB page 75. Answer the following question. Distinguish between conservative and non-conservative forces. Solution. Conservative force. Non-conservative force. 1. If work done by or against a force is independent of the actual path, the force is said to be a conservative force. If work done by or against a force is dependent of the actual path, the force is said to be a non-conservative force. 2. During work done by a conservative force, the mechanical energy is conserved. During work done by a non-conservative force, the mechanical energy may not be conserved. 3. Work done is completely recoverable. Work done is not recoverable. 4. Example. Gravitational force, magnetic force, etc. Example. Frictional force, air drag, etc. Exercises Q2. See page 75. Answer the following question. Distinguish between contact and non-contact forces. Solution. Contact forces. Non-contact forces. 1. The forces experienced by a body due to physical contact are called contact forces. The forces experienced by a body without any physical contact are called non-contact forces. 2. Example. Gravitational force, electrostatic force, magnetostatic force, etc. Example. Frictional force, force exerted due to collision, normal reaction, etc. Exercises Q2. XD page 75. Answer the following question. Distinguish between inertial and non-inertial frames of reference. Solution. Inertial frame of reference. Non-inertial frame of reference. 1. The body moves with a constant velocity, can be 0. The body moves with variable velocity. 2. Newton's laws are obeyed. Newton's laws are not obeyed. 3. The body does not accelerate. The body undergoes acceleration. 4. In this frame, a force acting on a body is a real force. The acceleration of the frame gives rise to a pseudo-force. 5. Example. A rocket in intergalactic space, gravity-free space between galaxies, with all its engine shut. Example. If a car just starts its motion from rest, then during the time of acceleration the car will be in a non-inertial frame of reference. Exercises Q2. X page 75. Answer the following question. State the formula for calculating work done by a force. Are there any conditions or limitations in using it directly? If so, state those clearly. Is there any mathematical way out for it? Explain. Solution. Exercises Q2. She page 75. Answer the following question. Justify the statement, work and energy are the two sides of a coin. Solution. 1. Work and energy both are scalar quantities. 2. Work and energy both have the same dimensions, i.e., m1l2t2. 3. Work and energy both have the same units, i.e., SI unit, Joule and CGS unit, erg. 4. Energy refers to the total amount of work a body can do. 5. A body capable of doing more work possesses more energy and vice versa. 6. Work done on a body by a conservative force is equal to the change in its kinetic energy. Thus, work and energy are the two sides of the same coin. Exercises Q2. She page 75. Answer the following question. From the terrace of a building of height h, you dropped a ball of mass m. It reached the ground with speed b. Is the relation mgh equals 1/2 mv2 applicable exactly? If not, how can you account for the difference? Will the ball bounce to the same height from where it was dropped? Solution. 1. Let the ball dropped from the terrace of a building of height h have mass m. During free fall, the ball is acted upon by gravity, accelerating conservative force. 2. While coming down, the work that is done is equal to the decrease in potential energy. 3. This work done, however, is not entirely converted into kinetic energy, but some part of it is used in overcoming the air resistance retarding non-conservative force. This part of energy appears in some other forms such as heat, sound, etc. 4. Thus, in this case of an accelerating conservative force along with a retarding non-conservative force, the work-energy theorem is given as decrease in the gravitational PE equals increase in the kinetic energy plus work done against non-conservative forces. 5. Thus, the relation mgh equals 1/2 mv2 is not applicable when non-conservative forces are considered. The part of the energy converted to heat, sound, etc. also needs to be added to the equation. 6. The ball will not bounce to the same height from where it was dropped due to the loss in kinetic energy during the collision, making it an inelastic collision. Exercises Q2. Sheet page 75. Answer the following question. State the law of conservation of linear momentum. It is a consequence of which law? Give an example from our daily life for the conservation of momentum. Does it hold good during the burst of a cracker? Solution. 1. Statement. The total momentum of an isolated system is conserved during any interaction. 2. The law of conservation of linear momentum is a consequence of Newton's second law of motion, in combination with Newton's third law. 3. Example. When a nail is driven into a wall by striking it with a hammer, the hammer is seen to rebound after striking the nail. This is because the hammer imparts a certain amount of momentum to the nail and the nail imparts an equal and opposite amount of momentum to the hammer. Linear momentum conservation during the burst of a cracker. A. The law of conservation of linear momentum holds good during the bursting of a cracker. B. When a cracker is at rest before the explosion, the linear momentum of the cracker is 0. C. When the cracker explodes into number of pieces, scattered in different directions, the vector sum of the linear momentum of these pieces is also 0. This is as per the law of conservation of linear momentum. Exercises Q2. XIV, page 75. Answer the following question. Define coefficient of restitution. Solution. For two colliding bodies, the negative of the ratio of the relative velocity of separation to the relative velocity of approach is called the coefficient of restitution. Exercises Q2. XV, page 75. Answer the following question. Discuss the following as special cases of elastic collisions and obtain their exact or approximate final velocities in terms of their initial velocities. 1. Colliding bodies are identical. 2. A very heavy object collides on a lighter object, initially at rest. 3. A very light object collides on a comparatively much massive object, initially at rest. Exercises Q2. XVI, page 75. Answer the following question. A bullet of mass m1 traveling with a velocity u strikes a stationary wooden block of mass m2 and gets embedded into it. Determine the expression for loss in the kinetic energy of the system. Is this violating the principle of conservation of energy? If not, how can you account for this loss? Solution. 1. A bullet of mass m1 traveling with a velocity u, striking a stationary wooden block of mass m2 and getting embedded into it is a case of perfectly inelastic collision. 2. In a perfectly inelastic collision, although there is a loss in kinetic energy, the principle of conservation of energy is not violated as the total energy of the system is conserved. Loss in the kinetic energy during a perfectly inelastic head-on collision. Exercises Q2. XVII, page 75. Answer the following question. One of the effects of a force is to change the momentum. Define the quantity related to this and explain it for a variable force. Usually when do we define it instead of using the force? Solution. 1. Impulse is the quantity related to change in momentum. 2. Impulse is defined as the change of momentum of an object when the object is acted upon by a force for a given time interval. Need to define impulse. 1. In cases when time for which an appreciable force acting on an object is extremely small, it becomes difficult to measure the force and time independently. 2. In such cases, however, the effect of the force, i.e., the change in momentum due to the force, is noticeable and can be measured. 3. For such cases, it is convenient to define impulse itself as a physical quantity. 4. Example. Hitting a ball with a bat, giving a kick to a football, hammering a nail, bouncing a ball from a hard surface, etc. Impulse for a variable force. 1. Consider the collision between a bat and a ball. The variation of the force as a function of time is shown below. The force axis is starting from 0. 2. From the graph, it can be seen that the force is 0 before the impact. It rises to a maximum during the impact and decreases to 0 after the impact. 3. The shaded area or the area under the curve of the force-time graph gives the product of force against the corresponding time, delta t, which is the impulse of the force. Area of ABCDE equals F delta t equals impulse of force. 4. For a constant force, the area under the curve is a rectangle. 5. In case of a softer tennis ball, the collision time becomes larger and the maximum force becomes less, keeping the area under the curve of the F, T graph the same. Area of ABCDE equals area of PQRST. Exercises Q2. XVIII, page 75. Answer the following question. While rotating an object or while opening a door or a water tap, we apply a force or forces. Under which conditions is this process easy for us? Why? Define the vector quantity concerned. How does it differ for a single force and for two opposite forces with different lines of action? Solution. 1. Opening a door can be done with ease if the force applied is A. Proportional to the mass of the object. B. Far away from the axis of rotation and the direction of force is perpendicular to the line joining the axis of rotation with the point of application of force. 2. This is because the rotational ability of a force depends not only upon the magnitude and direction of the force but also on the point where the force acts with respect to the axis of rotation. 3. Rotating an object like a water tap can be done with ease if the two forces are equal in magnitude but opposite in direction are applied along different lines of action. 4. The ability of a force to produce rotational motion is measured by its turning effect called moment of force, or torque. 5. However, a moment of couple or rotational effect of a couple is also called torque. 6. For differences in the two vector quantities. Moment of a force. Exercises Q2. Zix, page 75. Answer the following question. Why is the moment of a couple independent of the axis of rotation even if the axis is fixed? Solution. Exercises Q2. XX, page 75. Answer the following question. Explain balancing or mechanical equilibrium. The linear velocity of a rotating fan as a whole is generally 0. Is it in mechanical equilibrium? Justify your answer. Solution. 1. The state in which the momentum of a system is constant in the absence of an external unbalanced force is called mechanical equilibrium. 2. A particle is said to be in mechanical equilibrium if no net force is acting upon it. 3. In the case of a system of bodies to be in mechanical equilibrium, the net force acting on any part of the system should be 0, i.e., the velocity or linear momentum of all parts of the system must be constant or 0. There should be no acceleration in any part of the system. 4. Mathematically, for a system in mechanical equilibrium, n-ary summation F equals 0. 5. In the case of a rotating fan, if the linear velocity is 0, then the linear momentum is 0. That means there is no net force acting on the fan. Hence, the fan is in mechanical equilibrium. Exercises Q2. XXI, page 75. Answer the following question. Why do we need to know the center of mass of an object? For which objects, its position may differ from that of the center of gravity. Solution. 1. Center of the mass of an object allows us to apply Newton's laws of motion to finite objects, objects of measurable size, by considering these objects as point objects. 2. For objects in non-uniform gravitational field or whose size is comparable to that of the Earth, size at least few thousand km, the position of the center of mass will differ than that of the center of gravity. Exercises Q3. Page 75. Solve the following problem. A truck of mass 5 ton is traveling on a horizontal road with 36 km hr1, stops on traveling 1 km after its engine fails suddenly. What fraction of its weight is the frictional force exerted by the road? If we assume that the story repeats for a car of mass 1 ton, i.e., car moving at the same speed stops at a similar distance, how much will the fraction be? Solution. Given M truck equals 5 ton equals 5,000 kilograms, MCAR equals 1 ton equals 1,000 kilogram, U equals 36 kilometers per hour equals 10 meters per second, V equals 0 meters per second, S equals 1 kilometer equals 1,000 meters. To find ratio of force of friction to the weight of vehicle. Formulae. I. V2 equals U2 plus 2 is E. F equals ma. Calculation. From formula I. 2 times A truck times S equals version 2 U2. Therefore 2 times A truck times 1000 equals O2, 102. Therefore 2000 A truck equals 100. Therefore A truck equals 0.05 meters, S2. Negative sign indicates that velocity is decreasing. From formula E. F truck equals M truck times A truck equals 5000 times 0.05 equals 250 N. Exercises Q3. Page 76. Solve the following problem. A lighter object A and a heavier object B are initially at rest. Both are imparted with the same linear momentum. Which will start with greater kinetic energy? A or B or both will start with the same energy. Solution. 1. Let M1 and M2 be the masses of light object A and heavy objects B and version 1 and V2 be their respective velocities. 2. Since both are imparted with the same linear momentum. 3. The kinetic energy of the lighter object A. Exercises Q3. Page 76. Solve the following problem. As I was standing on a weighing machine inside a lift, it recorded 50 kilograms Wt. Suddenly for a few seconds, it recorded 45 kilograms Wt. What must have happened during that time? Explain with complete numerical analysis. Solution. The weight recorded by the weighing machine is always apparent weight and a measure of reaction force acting on the person. As the apparent weight 45 kgWt, in this case is less than actual weight 50 kgWt, the lift must be accelerated downwards during that time. Numerical analysis. 1. The weight on the weighing machine inside the lift is recorded as 50 kgWt, therefore mg equals 50 kgWt. 2. This weight acts on the weighing machine, which offers a reaction R given by the reading of the weighing machine, therefore R equals 45 kgWt equals 9/10 of a milligram. Exercises Q3. IV page 76. Solve the following problem. The figure below shows a block of mass 35 kilograms resting on a table. The table is so rough that it offers a self-adjusting resistive force 10% of the weight of the block for its sliding motion along with the table. A 20 kg Wt load is attached to the block and is passed over a pulley to hang freely on the left side. On the right side, there is a 2 kg Wt pan attached to the block and hung freely. Weights of 1 kg Wt each can be added to the pan. Minimum how many and maximum how many such weights can be added into the pan so that the block does not slide along the table? Solution. 1. Consider FBD for 20 kg Wt load. Initially, the block kept on the table is moving towards the left, because of the movement of the block of mass 20 kg in a downward direction. Thus, for a block of mass 20 kg, ma equals mg, T1. Opening parenthesis. 1. Consider the forces acting on the block of mass 35 kg in a horizontal direction only as shown in the second figure. Thus, the force equation for this block is M1 equals T1 T2F. Dot opening parenthesis. 2. To prevent the block from sliding across the table. M1 equals Ma equals 0. Therefore T1 equals Mg equals 200 N. Dot. From 1. T1 equals T2 plus F. Dot. From 2. Therefore T2 plus F equals 200. Therefore T2 equals 200 to 35 equals 165 N. Thus, the total force acting on the block from right-hand side should be 165 N. Therefore total mass equals 16.5 kilograms. Therefore minimum weight to be added equals 16.52 equals 14.5 kilograms. Approximately equals 15 weights of 1 kilogram each. 2. Now, considering motion of the block towards right, the force equations for the masses in the pan and the block of mass 35 kilograms can be determined from FBD shown. From the above third figure shows M1 equals T2 T1F. E. From the above fourth figure shows M2 equals M2G, T2. IB. To prevent the block of mass 35 kilograms from sliding across the table. M1 equals M2A equals 0. Therefore from equations E and IB. T2 equals T1 plus F. T2 equals M2 grams. Therefore M2 grams equals 200 plus 35 equals 235 N. Therefore the maximum mass required to stop the sliding equals 23.52 equals 21.5 kilograms approximately equals 21 weights of 1 kilogram each. Exercises Q3. B page 76. Solve the following problem. Power is rate of doing work or the rate at which energy is supplied to the system. A constant force F is applied to a body of mass m. Power delivered by the force at time t from the start is proportional to. Solution. Power is rate of doing work or the rate at which energy is supplied to the system. A constant force F is applied to a body of mass m. Power delivered by the force at time t from the start is proportional to t. Exercises Q3. B page 76. Solve the following problem. Derive the expression for power in terms of F, m, and t. Solution. Exercises Q3. B page 76. Solve the following problem. 40,000 liter of oil of density 0.9 grams per cc is pumped from an oil tanker ship into a storage tank at 10 meters higher level than the ship in half an hour. What should be the power of the pump? Solution. Exercises Q7 page 76. Solve the following problem. 10 identical masses, m each, are connected one below the other with 10 strings. Holding the topmost string, the system is accelerated upwards with acceleration g2. What is the tension in the sixth string from the topmost string being the first string? Solution. Consider the sixth string from the top. The number of masses below the sixth string is 5. Thus, FBD for the sixth mass is given in the following figure. The force equation for that mass is 5 Ma equals T5 milligrams. Exercises Q3. B page 76. Solve the following problem. Two galaxies of masses 9 billion solar mass and 4 billion solar mass are 5 million light-years apart. If the Sun has to cross the line joining them, without being attracted by either of them, through what point it should pass? Solution. The Sun can cross the line joining the two galaxies without being attracted by either of them if it passes from a neutral point. Neutral point is a point on the line joining two objects where effective gravitational forces acting due to both the objects is nullified. Given that the Sun has to cross the line from a point at a distance 3 million light-years from the galaxy of mass 9 billion solar mass. Exercises Q3. X page 76. Solve the following problem. While decreasing linearly from 5n to 3n, a force displaces an object from 3 meters to 5 meters. Calculate the work done by this force during this displacement. Solution. For a variable force, work done is given by the area under the curve of force V's displacement graph. From the given data, the graph can be plotted as follows. Exercises Q3. X page 76. Solve the following problem. Variation of a force in a certain region is given by F equals 6x to 4x8. It displaces an object from x equals 1 meter to x equals 2 meters in this region. Calculate the amount of work done. Solution. Exercises Q3. Sheet page 76. Solve the following problem. A ball of mass 100 grams dropped on the ground from 5 meters bounces repeatedly. During every bounce, 64% of the potential energy is converted into kinetic energy. Calculate the following. A. Coefficient of restitution. B. The speed with which the ball comes up from the ground after the third bounce. C. The impulse was given by the ball to the ground during this bounce. D. Average force exerted by the ground if this impact lasts for 250 ms. E. The average pressure exerted by the ball on the ground during this impact if the contact area of the ball is 0.5 square centimeters. Solution. Given that, for every bounce, 64% of the initial energy is converted to final energy. A coefficient of restitution in case of inelastic collision is given by Exercises Q3. Sheet page 77. Solve the following problem. A spring ball of mass 0.5 kilograms is dropped from some height. On falling freely for 10 s, it explodes into two fragments of mass ratio 1:2. The lighter fragment continues to travel downwards with a speed of 60 meters per second. Calculate the kinetic energy supplied during the explosion. Solution. Exercises Q3. Sheet page 77. Solve the following problem. A marble of mass 2 meters traveling at 6 centimeters per second is directly followed by another marble of mass m with double speed. After a collision, the heavier one travels with the average initial speed of the two. Calculate the coefficient of restitution. Solution. Exercises Q3. XIB, page 77. Solve the following problem. A 2 meters long wooden plank of mass 20 kilograms is pivoted, supported from below, at 0.5 meters from either end. A person of mass 40 kilograms starts walking from one of these pivots to the farther end. How far can the person walk before the plank topples? Solution. Let the person starts walking from pivot P2 as shown in the figure. Assume the person can walk up to distance x from P1 before the plank topples. The plank will topple when the moment exerted by the person about P1 is not balanced by a moment of force due to plank about P2. Therefore, for equilibrium, 40 times x equals 20 times 0.5. Therefore x equals 1/4 equals 0.25 meters. Hence, the total distance walked by the person is 1.25 meters. Exercises Q3. XV, page 77. Solve the following problem. A 2 meters long ladder of mass 10 kilograms is kept against a wall such that its base is 1.2 meters away from the wall. The wall is smooth but the ground is rough. The roughness of the ground is such that it offers a maximum horizontal resistive force, for sliding motion half that of normal reaction at the point of contact. A monkey of mass 20 kilograms starts climbing the ladder. How far can it climb along the ladder? How much is the horizontal reaction at the wall? Solution. From the figure, given that AC equals length of ladder equals 2 meters, BC equals 1.2 meters. From Pythagoras theorem. Exercises Q3. XVI, page 77. Solve the following problem. 4 uniform solid cubes of edges 10 centimeters, 20 centimeters, 30 centimeters and 40 centimeters are kept on the ground, touching each other in order. Locate center of mass of their system. Solution. The given cubes are arranged as shown in the figure. Let one of the corners of the smallest cube lie at the origin. As the cubes are uniform, let their center of masses lie at their respective centers. Therefore Ra is defined as 5, 5 RB is defined as 20, 10 RC is defined as 45, 15, and road is defined as 80, 20. Exercises Q3. XVII, page 77. Solve the following problem. A uniform solid sphere of radius r has a hole of radius r2 drilled inside it. One end of the hole is at the center of the sphere while the other is at the boundary. Locate center of mass of the remaining sphere. Solution. Let the center of the sphere be origin O, then r1 be the position vector of the center of mass of uniform solid sphere and r2 be the position vector of the center of mass of the cutout part of the sphere. Now, mass of the sphere is given as exercises Q3. XVII, page 77. Solve the following problem. In the following table, every item on the left side can match with any number of items on the right-hand side. Select all those types of collision. Illustrations. A. Elastic collision. I. A ball hit by a bat. B. Inelastic collision. E. Molecular collisions responsible for pressure exerted by a gas. C. Perfectly inelastic collision. E. A stationary marble A is hit by marble B and the marble B comes to rest. D. Head-on collision. IV. A blob of clay dropped on the ground sticks to the ground. B. Out of anger, giving a kick to a wall. B. A striker hits the boundary of a carom board in a direction perpendicular to the boundary and rebounds. Solution A. Elastic collision. E. Molecular collisions responsible for pressure exerted by a gas. B. Inelastic collision. I. A ball hit by a bat. E. A stationary marble A is hit by marble B and the marble B comes to rest. B. A striker hits the boundary of a carom board in a direction perpendicular to the boundary and rebounds. B. Out of anger, giving a kick to a wall. C. Perfectly inelastic collision. IV. A blob of clay dropped on the ground sticks to the ground. D. Head-on collision. E. A stationary marble A is hit by marble B and the marble B comes to rest. B. A striker hits the boundary of a carom board in a direction perpendicular to the boundary and rebounds.
Your place on fire.